Hi, everyone. I'm Debbie Moran. I'm the novice chairperson. I've been a member of the society since 1980 and probably learned everything I know about observing from being a member of the Houston Astronomical Society. And before I introduce our speaker, I'd just like to mention to new members that there are going to be things that you need to know now and maybe not in several months from now when we get back to covering it. So as a benefit of your membership, you can register at astronomyhouston.org. And once you log in, you will see a box at the right, and you can click on recorded HAS presentations. And virtually every topic at this point has been discussed, almost, except for tonight's celestial mechanics. And we have years of recorded presentations and should cover most of the things a novice astronomer needs to know. So for tonight, I'd like to welcome Justin McCullum, very longtime member of the Houston Astronomical Society. He's from Beaumont. He's been a instructor, professor at Lamar University in astronomy and physics, and is a wonderful lecturer. He was my predecessor as novice chair for several years here at the Astronomy Club. And Justin tonight is going to speak to us about celestial mechanics, or the motions of the bodies in the universe. And that should help you get a lot more context of what you're observing and how to find it in the sky and to understand how it's moving in the sky. So Justin, go ahead and take it away, please.
All right, so let me get to, let's see here. I want to be able to share that screen. Okay, here we are. All right, everyone see my screen here?
We do see it. And Justin, as we get going, I wanted to just remind everybody that if you have questions for Justin throughout the course of the meeting and presentation tonight, go ahead and use the chat feature that's built into Zoom here. Down at the bottom, you'll see a button that says chat. Go ahead and ask your questions there. I'll keep tally of those as we go through the night. And when we get to the end of the presentation, Justin, if you wouldn't mind, we can go through a few of those questions as well. Fantastic. Thank you.
All right, so this is, I call beginner's approach to celestial orbital mechanics. I've taught this class for several years at Lamar University in their area of space sciences. So what we'll do here is go through our fundamentals. There's Newton's laws of motion. Of course, Johannes Kepler developed his laws of planetary motion first. And then after a certain period of time, going from the 16th, 17th century, Sir Isaac Newton developed his laws of motion. We can relate the laws of motion to Kepler's laws of planetary motion. We have to remember that all bodies in the universe, whether it's a star orbiting another star of greater mass, or a planet orbiting around a star, or a moon orbiting around a planet, they all orbit in elliptical orbits, meaning instead of a nice circular orbit, you have an orbit that's in the shape of an oval. There's also what we call the Hoffman transfer orbit, that is going from an orbit close to the planet, to any planet, to a higher orbit further from the planet. So you can basically require less energy to travel to some other destination in the solar system. Also, there's Kepler's orbital elements. There's a series of different degrees and distances for which you try to track a satellite or a planet as it goes around the sun. If you don't get your elements right, you're going to miss observing the planet or a comet or an asteroid. You end up looking at the wrong area of the sky. Then there are the mechanics of the motion in the Earth-Moon system, how the Earth and the Moon orbit around the sun, how they orbit around, well, how the Moon orbits around the Earth, and the changes of those orbits over time. And then there's what we call it the perihelion precession of Mercury, because Newton's laws don't quite cut it when dealing with any body that orbits so close to the sun. It can't take into account how the orbit wobbles around a star, particularly when it's close to what we call the gravity well. That is, the gravity is so strong, the space-time around it gets what we call frame dragging, which means it can affect how the orbit is basically wobbling around the sun. And then if a body gets too close to a much more massive body, the tidal effects can tear a body apart. The same way, if there was a moon that once orbited Saturn, it got so close it literally was torn apart by the gravity of Saturn and forming the rings around Saturn. We call that the Roche radius. Now, we have to understand that there are Kepler's laws of planetary motion. The first law is simple. It's like taking a paper, it's like taking a cardboard with a piece of paper. You put two nails at a distance from each other. You wrap a string around the nails and around a pencil, and you draw an oval, an ellipse. the sun, and of course, those two holes represent where the nails driven in, they represent the foci. That's just the structure of an elliptical orbit. There are points at where you balance out the gravity between an orbiting planet and the star. Now, here we have the sun at one focus, and the other focus is going to be over here. Here's our planet, and it goes around this oval. 2A represents what we call the major axis, so that's the widest part of the orbit. The narrowest part is what we call the minor axis. Then if you take a line of a planet and you swing around a particular part of the orbit, it's going to cover a particular area. Now here, this area here where the planet is moving far away from the sun is going to be the same area as right here where we have the planet traveling along a greater stretch of that orbit. It's a much shorter distance, but the area here is going to equal the area there. So it sweeps out equal areas in the same interval of time. So let's say it takes this planet a month to swing across 30 Earth days to swing across this part of the orbit. It will cover this part of the orbit also in 30 days. Then here, when we talk about the semi-major axes, we're talking about the average distance of a planet around a star. So in this case, let's say this is the Earth or Mercury or Pluto. The average distance of that planet from the sun is going to be that semi-major axis. So for example, if we talk about how the sun is 93 million miles or 150 million kilometers from the sun, that's going to be the semi-major axis. Now we cube that value, and that's going to be proportional to the period squared. Here we measure this in astronomical units. That's the average distance between the Earth and the sun. And we can have multiple astronomical units for different planets orbiting at different distances from the sun. And the period square is going to be in proportion to Earth years. That is, how many Earth years does it take for a planet to orbit around the sun? Now here we got our three laws of motion. So a body at rest, that's the first law, will remain at rest, or it will be at a constant motion unless it's acted on by an external force. All bodies have a certain amount of mass. That mass is inertia. That's the resistance to motion. And in order to get that body to move, you have to use a force to get that body into motion. Or if it's moving, it moves at a constant speed, and you have to exert force to get the object to change its speed. The second law, I don't know how many of you are familiar with this, that's basically when you have a force acting on an object, it's equal to the mass of that object times its acceleration. So if you exert more force on an object and the object's mass remains constant, it doesn't change, the object will increase in acceleration. It will move faster and faster through space. And then the third law, simple, when we have a rocket going up into space, it emits exhaust, it pressurizes the atmosphere below it, pushes on the ground pushes to the atmosphere below the rocket's exhaust. The exhaust pushes the rocket up. So every reaction, there's an equal and opposite reaction. Now, the thing about Kepler's law, with Newton's laws and Kepler's laws, is realizing that any moon that orbits around a planet, any planet that orbits around a star, or any robotic vehicle that orbits around a planet or a moon, it's going to be in an elliptical orbit. Now, if the orbit is perfectly circular, there's not going to be two foci, only one, right here at the center. So the planet would orbit around at a fixed distance. So the eccentricity would be zero, which means it's a perfectly circular. But here, this is going to be greater than zero. In fact, as it becomes more and more elongated, the value will approach a number of one. And if it's one, it just simply becomes like a parabola. It just becomes a pathway. It swings around the sun, and then it goes out into the outer solar system, and then a few 100,000 years later, it will come back in a different path. Now, this is the semi-major axes. This is the semi-minor axes. Here's the sun at one focus. That's the gravitating body. Here's the planet. Here is the planet, and the way we have the arrows here, it goes counterclockwise around the sun. This represents from here to here, that shortest distance, that perihelion. Over here is going to be the aphelion. So this is going to be the greatest distance of the planet from the sun itself. And so this is just the basic structure of an orbit. Most orbits in the solar system and orbits around other stars, stars orbiting around other stars, and planets and other planetary systems are going to be in elliptical orbits. Now, that's the when we think about our laws, and this is actually Kepler's second law. The first law, we have that in the shape of an ellipse. All orbits are in the shape of ellipses. This is the second law. So we take this area here, this area right here. So these two areas are going to be the same. This arc length right here, which is the section of the circle, you can see it's longer than this section right here. When a planet is approaching towards the sun, it picks up energy as it gets closer to the sun. The force of gravity between the two bodies increases. The body picks up energy and it starts to swing around at a faster speed. As it comes around here, it's going to slow down just before it reaches this outer edge. And this is where it's going to be at its slowest velocity. So when we think about our Earth, it's not maintaining the same orbit. It's not maintaining, well, it maintains the same orbit, but it's not maintaining the same speed. The speed changes. Well, so when they talk about the orbital velocity of Earth, that's its average orbital velocity. It changes. It does accelerate not only inwards because the fact that we're using what we call centrifugal force, the force in which an object goes around in a circle, but that centrifugal force, in this case, is the result of the gravitational force, the force between the gravity of the planet intermingling with the gravity of the sun. And so there's an inward acceleration pointed towards the sun. But of course, we have to remember this planet is fighting against that gravitational field because all bodies want to move in a straight line. So as a result, this planet is falling into the curvature of the sun, but in this elliptical orbit. So there is what we call an angular velocity, meaning that the velocity of this body changes as it orbits around the sun. Now, this is just simply the formula that would be used. This is going to be the B represents that shortest distance in the ellipse. The A is the longest distance. If I take the this A right here for the semi-major axes, and I multiply that by the eccentricity, that's going to, of course, tell us about how elliptical the orbit is. This here represents the true anomaly, which means if these 2 points right here, what we call the apsido points, the points of aphelion and perihelion, if this was the sun right here, if these 2 points are lined up to some position in space, let's say like the constellation of Aries, then we look as this planet moves away from it, and that gives us an angle. And that angle is related to time. So if the planet is here, 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 and here, we need to know the time, the change in speeds. We know where that object is going to be as it goes around the sun. And it's going to be between 0 and 1. And if it's a 1, it's just going to be some pathway that goes around the sun at least once. Or if it's less than 1, if it's 0, it's going to be a nice circular orbit. But mostly you're going to have elliptical orbits. So the orbit is defined by the semi-major axes and the ellipse. So the greater the eccentricity, the more elliptical, the more these two foci are going to be stretched out. Position is defined by, of course, the orbital radius and that true anomaly. So we know where that position is with respect from this foci and that foci. And then the eccentricity describes the shape of the orbit. It's going to either be very circular, it's going to be more and more oval shape, or it's going to stretch out as a line. So that's our first formula. The second, of course, is looking how the planet swings around. So there's the change in area with respect to time, because it takes a certain amount of time, because the planet is moving at a certain velocity, the velocity changes. So there's a certain amount of time for it to cover this area. This is the velocity, meaning that it changes velocity as it goes around the orbit. We have the radius of the orbit that changes because of the planets at different distances from the sun. That 1/2 comes out of the math. Angular momentum is an object's susceptibility to move when it gives it energy. And that's regular momentum. That's traveling in a straight line. But we have the susceptibility for an object to go in a circular orbit around another body. And that's the angular momentum. In this case, it changes as the velocity changes. Now that deals with the momentum. We have the mass and the orbital radius. And this gives us our formula for Kepler's the first law, second law, where you're sweeping equal areas of equal time. So we have the change in the area over the change in the time. We have the angular momentum over the mass of the orbital body. and the 1/2 is just dealing with that kinetic energy. Kinetic energy is 1/2 mass times velocity squared. You're taking energy out of the field of gravity, and you're turning it into kinetic energy because you need that energy for an object to go under physical motion. Now, Kepler's third law, I'll go through this slowly. This here, mv squared over r, think of a hammer thrower. The hammer thrower in the Olympic Games has a hammer, speeds around in a circle, and also pivots around an invisible point. That is your centrifugal force, the force in which a body goes in a circle around another body. And we equal that to Newton's law of gravitation, where we have the mass of a big body, the mass of a little body, and the distance between them squared. But in this case, it's 1 over r squared, meaning that if I cut the distance between the Earth and the sun, I'm increasing the force by a factor of 4. If I double the distance from the original distance, so instead of half an AU from 1 AU to 2 AU, I've cut the force by a factor of 4, so it's only 1/4. That means it takes the planet a longer period of time to go around the sun, whereas here we can shorten the year in which the time in which it takes for the Earth to orbit around the sun. It would take less time. Then this here represents the velocity. That is, we're assuming that it's a nice circular orbit. R is the radius, the distance between the Earth and the sun. Then we get the t, the period, the time it takes for it to go around the sun, in which case this is going to be 1 Earth year, 365 days. This here represents the specific gravity, because with a body with a lot of mass, if it has a strong field of gravity, any body with a field of gravity, there's going to be energy stored for every piece of mass in the body itself. And so the sun is going to have a strong field of gravity because it has a lot of mass. There's a lot of energy which the Earth can take from that sun and use that as energy for it to go into an orbit around the sun. So this is going to be the period squared. And this r cubed right here really represents the semi-major axes, because we have to deal with the fact that we're in these elliptical orbits, not circular orbits. So we have the mass in the center. Here we can use this for the Earth. Here's the mass of our satellite, and we can apply the same thing to the Earth's moon orbiting around the Earth, or any satellite orbiting around the Earth. Here we can look at the change in time. Well, here's the change in time right here. This is squaring the time, the period it takes for each planet to orbit once around the sun. And this is cubing each planet's average distance from the sun. And this is a log-log plot, but it gives us a nice straight line. And that expresses Kepler's law of periods for the third law. Now here we have the period squared, the semi-major axis cubed. That semi-major axis is the average orbital distance. The semi-major axis is averaging the perihelion and the aphelion. So you add the two values, you divide it by 2, that gives you the average distance. Or the apsido points for any secondary body orbiting around a primary body. That is, if you think of the moon has a minimum distance, a perigee, and a maximum distance, an apogee. And the apsido points represents positions of when a body's at its closest and furthest distance around a central body, such as the Earth orbiting around the sun, or even one of the moons of Jupiter orbiting around Jupiter. So here's another look at this. So this is working this in such a way that here we can see the period in years. Here's a semi-major axis, 110, and we get this straight line here. So that means as a planet gets further from the sun, its period increases immensely. That is, it takes a lot more time for each planet further away from the sun to orbit around the sun. Now, the structure of an elliptical orbit, this was a very important advancement in astronomy and heliocentric cosmology. Now, Nicholas Copernicus thought of the planets as in nice circular orbits, but of course, Johannes Kepler looked at the data from a Danish astronomer, Tycho Brahe, and found that the planets are in these elliptical orbits. So this is our maximum distance here. Here's the aphelion in the case of the Earth orbiting around the sun, or any planet orbiting around the sun. And this is going to be the perihelion. So if you look here, we've got this distance here for the semi-major axes of the ellipse. Here's the eccentricity. And so if we take this A right here, that semi-major axes, and either if we add in this EA, that will give us the, of course, the planet's maximum distance from the sun. If we subtract that EA from A, that gives us the planet's minimum distance from the sun. So here we have the example of a pencil. We have two foci. We draw an ellipse right around the center of this ellipse, and we get the sun at one focus. And then along that ellipse, that's going to be the orbit of a planet. It can apply to dwarf planets and even comets. So it's very simple. Nice circular orbit. Now, a circle is basically an ellipse where the eccentricity is 0. In nature, ellipses are normal. The circle is the exemption. So you can see how the orbit is more spread out. It gets more and more oval shaped, and the foci are much further together. So if we imagine something like a comet, it's going to have an ellipse like this, but it will orbit around the sun maybe once every few hundred years or a few thousand years. You don't want the Earth to be like this, because then the Earth will get closer towards the sun than Mercury. So it'll be several hundred degrees Celsius. If it goes out here well beyond Pluto, it can be so cold the atmosphere freezes as ice on the surface. Now, in a little bit here, where you can take like a metal sheet and cut sections along a cone. So here we have the circle where the eccentricity is 0. Here's the ellipse. Here's the parabola. A lot of comets that are non-periodic follow a parabolic path. If it's greater than 1, it's going to have an eccentricity of 2. That's like the Oumuamua object that passed through our solar system, that extraterrestrial object. It was on a hyperbolic path. So it came through our solar system, and now from some destination in interstellar space, and it's now going out into interstellar space, never to return. So here we can look at the eccentricity. So we can see that Mercury has the most elliptical orbit, whereas Venus has the least elliptical orbit. Neptune has the second least elliptical orbit. And then Mars has the second most eccentric orbit after Mercury. Here's the orbital periods. Here's the orbital radius. And for that eccentricity, we can take the differences between maximum and minimum distance and divide that by adding the maximum in the minimum distance. So it tells us if the orbit's going to be very oval shaped, or it's going to be a nice circular orbit, or close to being circular. A lot of these orbits are close to being circular. So even in the case of Mercury, it's going to be a bit more circular than this, than where the eccentricity is 0.5. So there's something called the Hertzmann transfer orbit, where an object can go from a lesser orbit to a greater orbit further away. And that means changing the orbital velocity, what we call the delta V. So if you're going to go to an orbit far away from, let's say, from low Earth orbit to an orbit, let's say out in geosynchronous orbit, that is where a satellite takes 24 hours to revolve around the Earth, then you're going to need a lot of energy. You're going to need a lot of rocket fuel. So the more of a greater orbit that you need to, in order to get move further away from the Earth, like if you have to go from low Earth orbit and go all the way to Mars's orbit, you need a lot of delta V. You're going to have a huge that should be HOH there, a Hertzmann transfer orbit. And this is an application of Kepler's third law. So you're going to have to speed up the vehicle in order for it to travel out to the larger orbit, and then, of course, use more delta V to escape that larger orbit where there's less gravity that the satellite has to deal with from the Earth because it's further away, and then you can escape out to another destination in the solar system. You can also adjust the acceleration. You're increasing the acceleration here, but you can decelerate, particularly if you're dropping down into a lower orbit, particularly if you fly all the way to Mars, you want to get into Martian orbit, you want to decelerate, and that will drop you down into a lower orbit around, or into an orbit around Mars. So you have to have a negative delta V. So here we can see the difference between the two here is that I'm having this term be subtracted by this term. The R1 is the current orbital radius. And then you have that second orbit, which is the Hertzmann transfer orbit. And then here, we're going from the desired orbit to a much lower, well, in this case right here, this is going to take us towards periapsis in current orbit. That is, we can descend down to a lower orbit. Here, this allows us to ascend to a much higher orbit. So we can, if we want to go from a large orbit to a small orbit, we can then, of course, go with our current orbit at its closest distance and then travel down to an orbit of lesser altitude, lesser distance from a central body. In the case of a satellite or a spacecraft orbiting around Earth or any planet or any moon. And then it'll be the opposite when we're at apoapsis, when we're far away from the planet that we're orbiting, and we want to go to a further orbit. It's best to be at our furthest distance in our current orbit. That way we need less delta V, we need less energy. So we can think of the Hoffman transfer orbit. So we think of this example here using Mars. We've got a 26-month, we have 26 months between launch windows. That's longer. You see, it takes Mars 687 days to orbit once around the sun, but to get the Earth and Mars to line up perfectly for the shortest distance, for a good window, to have the minimum distance to travel from one orbit to the next, it takes a longer period of time. It takes 26 months. So we're looking at current technology, a 9-month journey from Earth to Mars using chemical propulsion, and then 9 months back, which means you're limited to about 8 months in Martian orbit and surface exploration. Now, a lot of missions are looking at scenarios of astronauts staying on the surface of Mars for 500 days, which means you have to cut this time by a third to about 3 months or 6 months. Actually, this will be more like 3 months instead of 9 months. So you don't miss that 26-month period between launch windows, because then if you're getting into 52 months, you're going to be spending more than 4 years in space, and you worry about all that heavy ion radiation and solar radiation if you don't have an artificial magnetic field around you or heavy shielding. So this is going from point 1 to point 2, and then you go around, you stay on the surface of Mars for a huge section of its orbit, and then you go from point 3 to point 4 back to the surface of the Earth. Now, orbital elements. This is the semi-major axes. I'm pointing this towards the galactic center. This is what we call the first point of Aries. A long time ago in antiquity, the constellation of Aries is where we had our spring equinox. Now, here we have a plane of reference. We can use this, for example, the plane of the Earth's orbit as the plane of our solar system. And here's the orbit of some body, some other planet, going around the sun. Here we have the inclination, so it gives us the tilt of that orbit of that planet with respect to our own Earth's orbit. Then there's what we call the ascending node itself, where the planet is ascending northward into the northern ecliptic hemisphere. So we have to realize that our solar system, we look at constellations along the zodiac, where that zodiac is the ecliptic. That's looking at the Earth's orbit across the sky, if you were to project that like you do in stellarium. So everything north of that is the northern hemisphere for the solar system. Everything below that is the southern hemisphere for the solar system. So this would be ascending into the northern skies of our solar system. This would be ascending into the southern skies of our solar system. And then, of course, we look at the position of this ascending node with respect to the reference direction. Of course, we're going counterclockwise around the sun in an eastward direction. And so we look at the angle here with respect to the 0 degrees going eastward or counterclockwise around the sun. That gives us our angle, our longitude of the ascending node. And then, of course, from that line right here where the orbit goes above to where the position is our shortest distance from the sun, that's what we call the argument of periapsis. And then there's the true anomaly, where from that shortest distance, we look at the current position of that body away from that shortest distance. All of that is important because if we don't have all these orbital elements, that is, all these properties to this orbit, we're not going to be able to find what we're looking for in the solar system. So we usually measure the semi-major axes of the ellipse in kilometers or nautical miles. A nautical mile, I think, is about 1.15 miles. So that's like a knot in the Earth's oceans. So if you're traveling at a speed of 1 knot across the ocean, you're traveling that's 6,072 feet for 1 nautical mile. The eccentricity of the ellipse, basically it's 1 if it's a straight line like a parabola, or it's 0 if it's a perfect circle. Greater than 1, the body, of course, can escape out into interstellar space. And then there's the angle between the orbital and the reference plane. So the reference plane in this case would be the plane of the Earth's solar system, and the orbit can be some other body other than the Earth. And the plane of our solar system is going to be the plane of our Earth's orbit. Then there's this argument of the pericenter or the periapsis. Basically, we draw a line to the vernal equinox to the ascending node right here, in which case where the planet that we're observing, or any body orbiting the sun, will ascend into the northern hemisphere of our solar system. Then there's the true anomaly. That's the angle between our periapsis, in which the body is at its closest distance to the sun, and the orbital body in its orbital plane. So if it's over here versus here, we have an angle, but we also have to measure it at a specific time, because we have to remember these bodies are taking a certain amount of time, measured in Earth time, as those bodies are orbiting around the sun. And the plane of reference, it doesn't have to apply to the plane of the Earth's orbit. It could be, we could decide to use the equator, the plane of the sun's equator, or we can use, in the case of any, well, I'll give you an example, like the Earth's moon is tilted at about 5 degrees with respect to the Earth's equator. And so that body is tilted, so we can use the equator, the plane of the equator of the Earth, as a localized plane. Now, the vernal point is known as the first point of Aries. That was located originally at the vernal equinox. Of course, now it's positioned in the constellation of Pisces. It's also known as the right ascension of the ascending node. Because we have to remember, we look in the sky, we've got coordinates, lines of longitude as right ascension. And wherever that right ascension intersects with that vernal equinox is going to be our 0-hour right ascension, where we see the sun crossing where the equator, the celestial equator, which is the equator of the Earth projected against the sky. And of course, we have the plane of the ecliptic where they intersect, and where the sun is ascending from the southern into the northern skies are going to be at that 0 hour. Now, there is something what we can call the RAN also the local time of the ascending node. And we have to remember where you're at on the surface of the Earth. People think of solar noon. They think, oh, at 12 o'clock, the sun is going to be at this highest point in the sky, due south. But no, I mean, the summertime, the sun will be at solar noon past 12 o'clock. And in the wintertime, it's at solar noon before 12 o'clock. So we have to remember that if we're dealing with what we call a fictitious sun, the fictitious sun at solar noon, we expect it to be, okay, due south. It's going to be at its highest point in the sky at zenith at 12 o'clock. But we have to remember that if we look at here, this is something what we call the equation of time. Up here, where it's positive, basically what's happening is that the sundial, when you're looking at solar noon on a sundial, you'll see the sundial possibly at maybe here, we see it as high as 17 minutes. So that means instead of seeing the sun overhead at, let's say, 12 o'clock, it may be at 11:43. So we see, of course, the shadowing taking place past 12 o'clock very early in the day, whereas in the summertime, it's going to lag behind, because then, of course, we don't reach solar noon until well past 12 o'clock. And to use that, you get your local mean time. Of course, you can take the Greenwich Mean Time and minus the time zone, which will be your local time, rather standard or daylight time. And that will give you your local mean time. So right here, we think where we at is going to be at 12 o'clock. But every quarter of a degree of longitude, you move east or west. When you see the sun overhead, over here, you say, no, it's 11:59, or here, it's 12:01. So it shifts about a minute when the sun is overhead at zenith, every quarter of a degree of longitude. So here, the sun is going to be ahead in the solar clock. We're going to see it at midday before noon. And here, it's going to be behind because, well, here it's actually ahead because it's 1 minute ahead. And here it's going to be behind because it's a minute behind the solar noon. And that's one of the effects of the change in the moon's orbit, because in the orbit of the sun around the earth, because the orbit of the earth around the sun, the orbit of the earth around the sun is wobbling around the sun. And there are changes in the tilt of the earth, which changes that solar noon. So we have to remember that the earth itself is being pushed along by the moon and the sun. It's causing the earth to wobble on its axis. So we have this 26,000-year precession cycle. So the vernal point will shift around all the constellations here of the equinox, all 13 constellations every 26,000 years. That's a shift of 1 degree every 73 years. So every 73 years, the vernal point will shift across the sky. So here, this image right here was back in, so this is the current vernal equinox, where it's located here in Pisces. And next year, it'll be at 10:32 a.m. our time, Central Daylight Time, on the 22nd of March. And we have to remember that in 68 BCE, the equinox was not here, it was way over here in Aries. So it shifted across the Pisces-Aries border back in 68 BCE, right around the time of Julius Caesar. Then, of course, it will shift from the constellation of Pisces all the way over here to Capricornus, and that will be in towards the end of the 26th century. Now, I've shown you here the changes in that equinox. So this is where we at, right? This is where we at in the past. So, and I did this with stellarium. So at 10:56 our time here in Texas, 22nd of March, 68 BCE, there was the sun right there. So right there as it passes from Aries into Pisces, there was the old vernal point. Here, of course, well, over here, this is where it crosses from Pisces into Aquarius on the 19th of March, 2579 CE at 6:09, at 18:0900 hours, 6:09 p.m. our time. And as we go further in time itself, we'll have it cross into the constellation of Capricornus. Here, of course, we're going deeper into Aquarius. This is in the 38th century. So March 20th, 3708 CE at 104 in the morning our time. What's interesting is that on this date, everyone see here, here's the Helix Nebula. It's lined up with the sun right on the vernal equinox. So on the first day of spring here, on this date in this year, in the 38th century, we're going to have at the time we have this vernal equinox, we're going to, of course, see the Helix Nebula right there in Aquarius. I thought it's very interesting. So the vernal point, the first point of Aries, that's our right ascension of the ascending node. Now then, we have to remember that there are some things that we have to use to point out the position of this body. There's something we call the eccentric anomaly. So we look at the angle here. Here is the direction of the periapsis. Here's the current position in the body's orbit as it goes around the sun. There's a better example of this right here, where we look at this from the center of the ellipse. Here's the line of that perigee. Here's the Earth. Of course, what we have to realize is if we're looking in the case, well, actually, this is the case here. If here's the Earth, and this is, of course, going to be a satellite. But let's say that this is the sun and this is the Earth. So we take the Earth currently where it's at right now in its elliptical orbit. Let's say that this is the sun rather than the Earth. And this, of course, is the Earth rather than the satellite. That true position from the perigee is going to be that true anomaly. That's the angle from here, here, and here. Now imagine if we took this body and we shifted to where we draw a nice circular orbit using this distance right here, this semi-major axis as the radius for a nice circle. So for a hypothetical circular orbit for the Earth. And that means looking at from this position in that circular orbit to the point of perigee, that's going to be for the mean anomaly. Now then, if we look at here, from that position in its current elliptical orbit, and then of course, if we shift it up here to this position in the Earth's ideal circular orbit, and then we look at the angle from this perigee, actually think of this as the perihelion. if this is the sun and that's the Earth. Then we look at this here from the center of this orbit. From that angle, from this line of perihelion to the position there in the circular orbit, that's what we call the eccentric anomaly. Now here I have this as the Earth and the satellite, so that would be the line of perigee. But if this were the sun and that was the Earth, then this would be the line of perihelion. It's very good to do this with both the circular and the elliptical orbit, not from just the position of a body in one foci of the elliptical orbit, but from the center of the ellipse, if it was with respect to a circular orbit. It takes into account any errors and any corrections that are necessary, particularly if you want to course correct the vehicle. You want to make sure you compare to elliptical and a circular orbit, because that way you can better get your body, your let's say your spacecraft, to reach your destination for some planet orbiting a star or some moon orbiting around a planet at the right time. And it all depends on the angle and the time itself, because that will change that position. That position changes as the angle changes with time, because the distance changes. So here, despite different velocities, here we can see both planets reach the point of perihelion at the same time. So if we compare, this is our actual planet. This is the idea for our planet's orbit. And so here we reach the true anomaly when we're at aphelion or perihelion, but we can see how that true anomaly differs from the mean anomaly. Now, looking at the mechanics of the Earth-Moon system. So we have to remember that the moon is in synchronous rotation with the Earth. That means we have the same side facing the Earth the whole time, the same hemisphere. This is the near side, which of course we call the trailing hemisphere. The other side, the far side of the moon, we never see. It's what we call the leading hemisphere. Because as the moon rotates on its axes, it's going around. See, the moon rotates eastward around its axes. And the moon itself is orbiting counterclockwise around the Earth, so it's shifting in an eastward direction. So the far side of the moon is rotating in the moon's orbit, in the direction of the moon's orbit around the Earth itself. So we call that the leading hemisphere. And the near side of the moon is trying to catch up with the far side of the moon as the moon spins on its axis. So we call that the leading hemisphere. Now we have to remember that to go from new moon to new moon, that's going to be what we call the synodic or the lunar month. Whereas the sidereal month is going to be when the moon completes one orbit around the Earth itself. So remember, to go from new moon to new moon, the moon has to orbit more than once around the Earth. The near side always faces the Earth, the far side never faces the Earth. But of course, the far side and the near side will both see the sunlight. So we have to remember that everything in the solar system is skewed. For instance, let's look at the plane of the ecliptic here. So this is the plane of the Earth's orbit. This, of course, is the tilt of the moon's orbit. Of course, the tilt is much greater. I said 5.1 degrees with respect to the Earth's equator. It's actually with respect to the ecliptic plane. Here, of course, represents the tilt of the Earth as it's pointed towards the sun. And we can see, of course, the tilt of the moon's orbit is a lot greater. And of course, we not only see that the Earth itself is tilted in its orbit around the sun, but the moon, of course, is tilted in its orbit as it goes around the Earth. Now, there's only 2 points, because the orbit is tilted, there's only 2 points in when the moon's orbit crosses the Earth's orbit. And that's known as the line of nodes. And those line of nodes are shifting around the Earth. Now, if the moon's orbit is nicely lined up with the Earth's orbit, that is, if there was no tilt in the moon's orbit, if it was nicely lined up with the ecliptic plane, then anywhere on the Earth's surface where there is a new moon or a full moon, you would see a solar or a lunar eclipse. And that's only going to happen when the line of nodes line up. So it's not always, that's one of the reasons why we never get a solar or a lunar eclipse, because we're at the mercy of when those lines of nodes are shifting around the Earth, so we get 2 points in the moon's orbit that will line up with the plane of the ecliptic. Now, the moon's orbit is also imperfect. It actually wobbles around the Earth, but it also changes in its shape. So here, the perigee, it changes by about 8,694 miles. So when the moon is at its closest distance to the Earth, it varies by a distance that is larger than the diameter of the Earth. The apogee range, the position of its furthest distance from the Earth, shifts by about 1,700 miles. So that's more than twice the width of Texas from the Sabine River to El Paso, or nearly twice that distance. So here what we get is that the moon is actually doing two motions. One thing is that it orbits around the Earth, but you see it orbits around the sun, but in this sort of wave pattern right here. So we get what we call these cusps and cycloids. The cusps right here represent the moon itself as it orbits around the Earth, and of course the cycloids here is the Earth itself. So we have to remember that the moon and the Earth are wobbling around each other. Here, of course, we have the barycenter. That's basically the Earth is wobbling around a center of mass where the gravity with the Earth and the moon are balanced out. So as the moon is orbiting around the Earth is wobbling around that barycenter. So let's say if the barycenter was here, and let's say Asia was on the dark side, that means most of the people are actually further from the sun than at that point of the barycenter in the Earth's orbit as it goes around the sun itself. Whereas if North America was on the dark side and the barycenter was over here, then us in North America are further from the sun than the Earth's current position in the orbit, in its orbit around the sun. So really the Earth's orbit is actually the Earth-Moon orbit. So we talk about 365 days, it's 365.25 days in which the Earth is orbiting around the sun. That's actually the orbital period for the Earth-Moon barycenter. So it takes 13.3 sidereal lunar months for one sidereal Earth year, and it takes 12.4 synodic lunar months for one sidereal Earth year. So that means this is the time in which the moon, so the moon will orbit around the Earth 13.3 times before the Earth, and the same time it takes for the Earth to, the time it takes for the moon to orbit 13.3 times around the Earth, that's the same time it takes for the Earth to revolve around the sun. And then for the moon to go from new moon to new moon or from full moon to full moon, it'll do that 12.4 times. And by it reaches that 12.4 times, that's the same time it takes for the moon to go with the Earth at least once around the sun. So this is the apsidal precession. So it takes 3,233 days for the moon to wobble once around the Earth. So we lined up that position, the point of its furthest distance from the Earth, the moon's furthest distance from the Earth. And if we line it up with a constellation like Taurus, that position across the constellations is going to shift. Now, this is what we call the nodal precession. Now, the nodal precession, of course, where the moon's orbit, the line of nodes that crosses the plane of the Earth's orbit. So the moon will ascend. So we have the ascending node as it goes above the plane of the Earth's orbit. And then there's the descending node where the moon goes below the plane of the Earth's orbit. Now, we have to remember it's weird because here, if we look at the apsidal precession here, the moon's orbit is wobbling counterclockwise around the Earth, but the sun orbits counterclockwise around the Earth. Now, the line of nodes is actually shifts clockwise, so it's going the opposite direction. It moves westward across the sky while the moon and the moon's orbit, while the moon itself orbits around the Earth and the moon's orbit is wobbling eastward counterclockwise in the opposite direction. So we get this 360-degree shift every 6,798 days. That's 18.6 years. That falls into the cycle, what we call the draconic month or the nodal period, where we get our eclipse cycle, our cycles of lunar and solar eclipses. So here is the moon's node moving westward. So we get a nodal period that's actually less than the sidereal period. So the nodes are taking less time to shift around the Earth than it takes, of course, for the moon to orbit once around the Earth in the opposite direction. So there's a difference in that nodal period versus sidereal period. So here we get the moon going in this direction, but the moon's node is going westward. And it's very important with those line of nodes shifting around, because you could have the line of nodes right here where we're having first quarter and last quarter moon, and you just have to have the line of nodes lined up perfectly at a right angle to the moon's orbit. Otherwise, you're never going to get that new moon solar eclipse and that full moon lunar eclipse. So this is pretty much like a top, because we have to remember that the moon is actually pushing against the Earth with tidal bulges. The moon's orbit is at an angle, so the tidal bulges between the Earth and the moon are not lined up. And that's actually causing the Earth to actually sort of wobble around the circle, the same way a top spins around itself as that top is wobbling around another circle. It does it, of course, for the moon itself. So we have the moon's bulging going upwards. There's the gravitational pull pulling down. We can have the moon up here. We have the tidal bulges not exactly lined up with the Earth's equator. And that's causing the Earth to wobble around like a top. This is what we call this nutation. Because the moon's orbit is tilting up and down, the moon's axial tilt will change. And that will change what we call the obliquity, which is changing the axial tilt of the Earth itself. This is the precise date for the precessional period. There's the nodal period. This is the change in the axial tilt. So it can be as shallow as 22 degrees. It can be as steep as 24.5 degrees. So this can create patterns, changes in the weather seasons and in the climate of the Earth in its orbit around the sun over long periods of time. There's actually what we call the Milankovitch cycles, where every 41,000 years, you get a cyclical change in climate and weather patterns that can induce ice ages or long warming periods, like the current warming period that we're in right now. So this can affect both the interglacial and glacier periods and can accumulate over thousands to millions of years. So you get a change in the Earth's shape of the Earth's orbit. You can also have a change in the axial tilt. When the axial tilt changes, that's the change in the obliquity. There's something here what we call the climatic precession, which deals with changing the position of the Earth from its distance from the sun during the summer solstice. And here this deals with what we call the eccentricity, that is changing the shape of the Earth's orbit around the sun and changing the position of its perihelion as an angle. That is the line of its perihelion, the distance, the shortest distance between the Earth and the sun with respect to the position of the vernal equinox, with respect to the constellations in the zodiac. Now, all this shows here is that the eccentricity, the shape of the moon's orbit, is changing over time. This is the obliquity, which of course is shifting the axial tilt of the Earth. So right now, our axial tilt during summertime is pointed away from the sun while we are at aphelion, our furthest distance from the sun. But there can be cases where we're at our closest distance to the sun and the axial tilt is pointed towards the sun rather than being, well, it's pointed towards the sun during the summertime where we're at our furthest distance from the sun. But the change in the orbit could bring us towards our closest distance towards the sun, and we could have the axial tilt pointed towards the sun, and that means longer and even hotter summers than what we're facing. And if we have the axial tilt pointed away from the sun, instead of at our closest distance towards the sun currently, we're at our furthest distance from the sun, it means a lot colder winters, perhaps more like that of Canada. And this is the precession right here, which deals with changes in the way in which the Earth's axial tilt is wobbling, and also the change in the shifting of the Earth's orbit as it shifts around the sun itself. So this, of course, represents the change in the axial tilt. This is the change of the eccentricity, so the Earth's orbit will wobble. Negative, of course, deals with errors in the formula, but technically it goes from 0 to 0.05. Reason why it's negative, because you can flip the position of the current position of the perigee and the apogee. Longitude of perihelion basically goes from 0 to 300, from 0 to 180 degrees, whether you're going from where the orbit crosses, let's say, the plane of the ecliptic, descending down into the southern hemisphere of the Milky Way galaxy, and ascending upwards into the northern hemisphere. I'm sorry, the southern hemisphere of our solar system when it's descending, and then ascending as it crosses the plane of the ecliptic into the northern hemisphere of our solar system. There's the precessional index. That index changes. It changes what we call the insolation of, or the solar irradiance. That means as the Earth orbit changes, as it shifts and it changes that axial tilt, it can have a huge effect in the amount of radiation we receive from the sun. Right now, we're about 567 watts per meter squared, the maximum amount of wattage for every square meter of solar panels for solar power, but it can be as low as 400. It can be as great as 600. So we could have incredibly hot, long summers or incredibly cold winters. And this black line right here represents that change in the insolation at the summer solstice around 65 degrees north latitude. And this is over thousands of years in AD. So this goes back 800,000 years to the present. And this looking at the ice core, changes in the temperature of the ice from looking at the weather from ice cores taken in the Antarctic plateau, from the Vostok base in Antarctica. And this deals with these microorganisms, fossils going back hundreds of thousands of years, and that's just the isotope of oxygen. And it correlates very well to the changes in the orbits of the Earth itself that wobbles around the sun for long-term changes in both in the weather and climate patterns. So here is the change in the precession of the orbit, the shape of the orbit over 600,000 years. Here's the change in the eccentricity. So the precession, of course, changes the rate at which the Earth orbit is wobbling around the sun. This is, of course, changes in the shape of the orbit over 600,000 years. And this is changing in the tilt of the Earth over 600,000 years, from being below 22 degrees to being around 24.5 degrees. So, of course, as the eccentricity changes, we can go from a nice circular to a very elliptical orbit, currently than what we have now. And the tilt itself, the obliquity. So if you think it's hot in the summer right now, think what would happen if the tilt was greater than our current 23.5 degrees. If it goes to 24.5 degrees, and let's say in the summertime we were at perihelion versus aphelion, then we would have almost like Amazonian-like weather versus what we have right now, very ultra hot tropical weather versus the weather we're having right now. Whereas if the axial tilt itself is a lot shallower, then we have more milder summers. We have people more like the northern hemisphere, like Canada, during the month of August. Here, the change of the precession. So think what would happen here if our winter time was happening here, right here. We can think of what's happening here. Our winter time right now is currently right here at perihelion. But if it happened here at aphelion and we were at winter time, if we were truly at our furthest distance from the sun with even this greater maximum tilt, then we could have Canadian-like weather here in Texas versus the milder weathers that we have right now. So today we got our summer in June, our winter in December, our spring in March, our fall in September. 11,000 years ago, we can see where we have the fall in September. Here's the spring, here's the winter, here's the summer. But we can see how the seasons have flipped opposite from each other. And if we go into the future itself, we're seeing how the seasons are shifting around. So here is summer, here is winter, and we see how they flip around and flip around. So they're shifting like this: 2000 AD, 7000 AD, 12,000 AD, 17,000 AD. So we see the winter flipping, flipping, flipping. And that means that the seasons are shifting counterclockwise around the sun, because the Earth's orbit is wobbling counterclockwise around the sun. So here are some nice videos. So to the left, we can go into the future. You can see We can predict how the moon's orbit is shifting around the Earth. And over here, we can see an example of the Orbital precession, where when the Earth is at its furthest distance from the sun, we can see how that line is shifting around the sun itself. So that changes the way we would see the positions of constellations during certain seasons, during, of course, through thousands of years. So in the future, we would have Orion as a summertime constellation and Sagittarius as a wintertime constellation. Now we have the perihelion precession of Mercury. This is a case where we use general relativity. We notice that when we try to measure the change in the orbit of Mercury with respect to just Newton's laws, we end up being off by several degrees. So it's a difference between seeing Mercury in the telescope and missing it altogether. So this is the shift in arc seconds per century in terms of the fact we got 360 degrees each, of course, here 360 degrees, each degree is 60 minutes, each minute is 60 seconds. So we got 1,296,000 arc seconds for 360 degrees. So around Julian centuries, that is, you can say 30,160.6 Julian centuries. So that means when this position here of perihelion is shifting around the sun for Mercury, it's changing every 3,016,057 years, 260 days, 80 hours, 38 minutes, 15.555 seconds. Think about general relativity, you can predict this down to the millisecond. That's the formula. So this is the orbital period. That's the speed of light. And of course, here we have the eccentricity, and then the semi-major axis is going to be that average distance between the perihelion and the aphelion, taking the two distances and dividing it by 2. Now we can actually predict this, so we can see how many times that the orbits for each planet has wobbled around the sun. So here's going from Mercury to Neptune. This is the semi-major axis in AU. Here's the orbital period. So we go from 0.24 years to 164.8 years for Neptune. Here's the orbital inclination. Of course, the Earth is at 0 degrees. So we look at the tilts with respect to the Earth's orbit. Here's the eccentricity, the shape of the orbit. Now, at the precession, here we have this observed. This is based on general relativity, so we can calculate the average. Now, we don't have any observed for Uranus and Neptune because we haven't observed them long enough. Here we've seen these planets over thousands of years, the classical planets from Mercury to Saturn, but Uranus and Neptune were unknown until the 18th and 19th century. So we can calculate based on general relativity. Of course, here my average is the same as the general relativity because we don't have any observed data. For the number of orbital shifts to complete 360 degrees around the sun, Mercury has already done it 3,069.6 times over the period of the 4.5 billion years that our solar system has existed. But Neptune, to complete the same thing, would have to go around the sun over nearly 1.7 billion times. Now here's the period of precession. This is in million Earth years. So for Mercury, it takes a little over 3 million years for Mercury's orbit to shift around the sun. For our Earth, it's 25.92 million years. For Mars, it's about 95.126 million years. You get around Jupiter and Saturn, look what Jupiter. Well, here's Jupiter, 1.8 billion years. Oops, sorry. Here's Saturn, 9.26 billion years. Uranus, 54 billion years. Neptune would have to take over 166 billion years for its orbit to wobble once around the sun. And look at the number of complete perihelion precessions since the beginning of the solar system. Our Earth has wobbled around the sun 176 times. Neptune has only done it for like 0.027 times. And that's based on the start time of 4.56 billion years. And that's based on looking at the oldest radiometric dating of lunar rocks and meteorites that have survived atmospheric entry, meteoroids that have survived atmospheric entry and become meteorites on the surface of the Earth. Now, we have to remember that there are what we call, with the Roche Roche radius or limit, there's the idea of centrifugal effects and orbital motion, because we have to remember, in reality, ideally, we want to treat all bodies as rigid bodies, as if they were solid bodies. But in reality, all planets have solid and liquid components. Gaseous giants, the hydrogen atmosphere is going to turn into liquid. And when we have tidal bulging, it's common among any natural satellite orbiting a home planet or any planet orbiting around a star. So if we get a planet orbiting too close to a star, it's going to tear apart and form a ring of debris around that star. The same thing, if a moon gets too close to a planet, it will tear itself to pieces and form a ring around the planet itself. Now here we get a small little moon. The bigger planet isn't wobbling as much, but in the case of binary stars, we can see how that barycenter is shifting further and further out. This is more like Pluto with Pluto and Charon. This is going to be like two stars of equal mass, whether in a circular orbit or two elliptical orbits in which the foci of either orbit overlap. And as you decrease distance between the moon and the planet, or a planet around a star, the gravitational force gets greater and the tidal bulge increases. And so what do we get? Well, we have the effect of a body here getting too close. It stretches outwards. There's that difference in the gravitational force between the two sides. The body tears itself apart. It's spiraling around and forms a ring of debris. Let's say in the case here of a planet getting too close to a star or a moon getting too close to a planet, the same way you had probably a 60-mile diameter moon that once orbited around Saturn, it got too close, broke itself apart and formed the Saturn's rings. Now here we can do this for the Roche limit. We do this for a body that's completely solid. We do it for a body that is completely fluid. So we have to remember that if we have a body that gets too close, a massive body that gets too close, it's going to be torn apart. So in the case of the Earth, here is the Roche limit when it's a fluid. Here's the Roche limit if it's more of a solid object. So if you get too close to a body, then of course, if we do this in comparison to the moon with an average comet, let's say with the Earth, Jupiter, the moon, the average comet, if any of these bodies get too close to the Earth or to the sun, then of course, in the case of a comet, if it gets too close, if it's rigid, and it gets closer than this distance, it's going to be torn apart. If the moon got any closer than 492 kilometers, it's going to get torn apart and form a ring of debris. If our Earth gets this close towards the sun, it will be torn to pieces. Same thing with Jupiter. Same thing with the moon if it's close to the sun. And of course, with an average comet, it gets torn apart by the sun. It's more susceptible to the gravity of the sun itself, so it can be torn apart at a greater distance. A bigger body can be closer. Of course, if it's very, very fluid, it can also be torn apart. So it's a balance between both the rigid and the fluids. And it's just a basic equation. You've got the mass of the primary body, the mass of the secondary body, and of course, you got the radius of the secondary body. So it all depends on the mass of the body, you know, if it's completely liquid, if it's completely solid or somewhere in between. And that will dictate how close it needs to be towards the bigger body, the lesser body towards the bigger body for it to be torn to shreds. And that concludes our lesson.
A lot of great information there, Justin. Thank you so much. We did have a couple of questions that came up in the chat room.
Okay.
First was Krishna. Krishna, do you want to come off mute and ask your question? I'll give Krishna another second or so.
Well, I notice his question is the ice age due to the precession of the Earth's orbit? It could be, well, there are many effects, but it will play a part in the precession of the Earth's orbit does play a part in the ice age, because there's a change in the amount of radiation that the Earth will get from the sun, but also the axial tilt will change as well. So if the axial tilt is very shallow and we happen to be at our furthest distance from the sun, then that could lead to, of course, a greater ice age, but also the period of geological quiescence where you don't have a lot of volcanism taking place.
Great. Thanks for the answer. And then Ua, do you want to come off mute and ask your question?
Yeah, just thanks for the presentation, Justin. Yeah, just wanted to know the Kepler's laws. Is there any known successful reformulation of Kepler's laws or equations for a two-star planetary system?
If we get the planets orbiting around the two stars rather than orbiting one of the stars, yes. We can also do that with multiple. You can do that with one star orbiting around another star. If a planet is orbiting one of the stars in a binary system, it has to orbit very close to the star. Otherwise, it's in an unstable sort of a Lajuce, which is like a fancy figure-8 orbit, which gets into a lot of complicated Lagrangian mechanics. I don't want to address that because it's very complicated. The only time where general relativity takes place is if the body is orbiting so close to the star. If a planet or a star is orbiting too close to a more massive star, then you have to deal with the frame dragging, and the Newtonian laws literally fail.
They break down. Okay. And then something that I wanted to ask, it's when the reformulation of these Kepler's laws, does it take, do they use perturbation techniques? Just asking them, does it involve some kind of non-linearization?
No. That mathematics came with Lagrangian mechanics about a century later.
Okay. Thank you.
You have to remember, Kepler only worked, this was before Newton's laws of motion. So Kepler was devising these formulas before Newton actually founded physics.
Okay.
And that's the last of the questions we had in the chat room. Does anybody else have any questions for Justin? You can go ahead and take yourself off mute now and ask them yourself.
Joe, can I ask one more question, Joe, if you don't mind?
Well, certainly.
Oh, sorry about that. Somebody else can go ahead of me. Sorry about that.
I see Bill Spitzeri is off of mute, and I think he might have a question. We can't hear you, Bill.
Let me go to Bill. Bill?
You're off mute, but we don't hear you.
Hey, Bill, why don't you type the... Okay. On the shoulders of giants. So he's probably talking about Tycho Brahe and Johannes Kepler, pioneers of modern astronomy. Of course, both men lived around the time, close to the time of Galileo Galilei. And you have to remember that Tycho Brahe actually had an observatory. He didn't have a telescope, but he had instruments in which he could map the position of the planets and the stars across the sky. He had tables and tables of data, and that data itself was used by Johannes Kepler to derive his laws of planetary motion.
Hey, Bill, if you want to try disconnecting the audio and then reconnecting and see if that comes up. But in the meanwhile, Ua, I think you had another question you wanted to ask.
No, I was just going to ask could you please elaborate on this tidal lock between the Earth and the Moon system, and how I don't know if you could elaborate on that. I knew you did make mention about the fact that we only see one side of the Moon, but yes. I don't know how that relates to the tidal lock, the mechanism of tidal locking between planetary bodies.
Well, whenever you have, here's the thing, the Earth and the Moon are not entirely rigid bodies. They're actually stretching, because what happens is that the Moon is pulling on the Earth and the Earth pulls on the Moon. It causes the Moon to flex. It actually causes the Moon to bulge outward like this, and the same thing with the Earth. And if those bulges are lined up, there's what we call static equilibrium, which is like force and torque. And it forces one side of the Moon to always face the Earth. Now, it doesn't mean that the Moon itself always has one side. It doesn't mean that the Moon itself doesn't rotate once around its axis. It does that, but it does it less than it takes for the Moon to orbit once around the Earth. Now, the tidal bulges is simply the result of the two bodies pulling on each other because of the distance between the two bodies, and you have the force exerting over a distance between the two bodies, and it will cause these bulges to occur. And so you get one bulge that's that's literally pulling on the moon. There's another bulge flexing outwards. And it's the same thing on the moon on the other side. And so you get one hemisphere facing towards the moon. I mean, you got one hemisphere of the moon facing towards the Earth, and the moon will orbit around the Earth itself. And sometimes the bulges don't line up. Sometimes they're askew, so it causes the moon to librate. So we see a little bit of the far side of the moon. So it sometimes oscillates back and forth like this.
Okay, thank you.
Okay, Bill, do you want to try it now? Not working? Okay.
Hey, Bill, send me an email and I could answer your questions.
All right. Well, are there any last questions before we wrap up tonight's call?
Going once?
Going
Going
twice?
twice?
All right. Justin, thank you so much for the presentation tonight. It was very informative. I felt like I was back in college. So I had a wonderful time. Thank you.
Thank you.